तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so we have been discussing the high electron mobility transistor with L-gas gas structure, because this is the most popular structure because of the ability to have L-gas on gas. Now, we have gone through the entire physics behind this, how it works, etc. And just like in the case of MOSFET, the structure is almost similar to MOSFET in one sense, in another sense it is similar to MESFET. If you just take only the top layer, N plus source contact, N plus drain contact, then doped aluminum gallium arsenide, that is equivalent of the MESFET. But we disable the MESFET here by putting gate on this, which actually depletes the entire layer. Okay. So, you have got, when you deplete that, and also when you have this doped aluminum gallium arsenide on gallium arsenide, you have got a two-dimensional electron gas here. So, it is these electrons which we are actually using for current transport. And to ensure that this layer, the top layer, heavily doped layer, does not participate in the conduction any portion of the device operation, you ensure that there is a whole entire layer is depleted. Okay. So, what we have computed also is, we have seen that the voltage required to deplete this entire top layer will be VBI minus Vp0, which actually is equivalent of the threshold voltage of this top layer, just when it is depleted. Now, because of the presence of N plus layer on undoped gallium arsenide, you have this knot layer, and we also said that there are electrons here due to additional band bending in this layer, corresponding to delta Ec by q or delta Ec, the notch, there are electrons here. Now, what we are telling is, you can actually remove these electrons, in the sense wipe out those electrons from that region by forward biasing this junction, which actually is plus here minus here. So, when you apply total voltage to the gate, which is equal to VBI minus Vp0, which will deplete the top layer, additional negative voltage, which is actually delta Ec by q, if you apply, this layer will be depleted. In the sense, it is just in the verge of conduction. So, what we say is, the threshold voltage of that device, or the off voltage of the device, will be given by VBI minus Vp0 minus. Please remember, VBI minus Vp0 by itself has a polarity. For example, if VBI is larger than Vp0, this is positive. That is what we saw enhancement type of MESFET. If VBI is less than Vp0, this quantity will have negative. So, V off will be the negative quantity minus another positive quantity, that is it is negative. So, you can rest be assured that if VBI minus Vp0 is negative, you have a device with V off, that is equivalent of V threshold voltage, which is negative, that is a depletion type of device. Okay. Now, you can make this as an enhancement type of device by making this quantity positive. It will be more positive than delta Ec by q. How do you make this more positive? We make it more positive by making this less, Vp0 less. So, making the A layer, L-gas layer thinner, you can actually make this layer more positive. Okay, now, so the entire theme of the whole thing is device-HEMT is, you can have depletion type of device or enhancement type of device. Whatever be the thing, the operation of the device is similar to MOSFET. You can see the difference. In the case of MOSFET, P channel P type substrate, n plus source n plus drain. Between the gate and the substrate, what do you have? You have SiO2. An insulating layer with epsilon r equal to 4. In the case of HEMT, what do you have? You have a semi-insulating gallium arsenide. I am referring to gallium arsenide because this is the device that we are talking about right now. Then undoped gallium arsenide, undoped, okay. And on the top of that you have got this Al gas. So, what you have now is a doped layer, undoped layer, which I have already put there. In fact, this will give rise to the two-dimensional gas. That diagram already we have been discussing. So, you have this n plus here, you have this n plus here, and you have a gate here. So, I can call this as the gate in the case of MOSFET, this is a gate in this case of MOSFET. The difference is this is metal oxide semiconductor, this is metal semiconductor contact, a Schottky barrier, but you ensure that the thickness, doping etc. is such that the built-in potential itself will deplete the whole thing. So, you do not want this to conduct. So, now when I apply a voltage in the gate and the source, this is depleted. So, this entire layer is equivalent of that, and this layer can be made 0.1 micron or even smaller. This layer also can be made 300, 400 angstroms, very thin. Added thing here is, so this is actually almost equivalent of this, or it is exactly equivalent of that. You have got notch here, I have discussed earlier. Recall the p channel thing, that is the oxide, and then you have got the Fermi level, you have got the band bending taking place like that. So, that is where the electrons are notch held up, that is the electrons here, inversion layer. Threshold voltage is the voltage at which it becomes band bending is such that it becomes n type completely. Okay. Here what you have is similar notch, the conduction band. I am plotting only this one here, that is the conduction band notch, and from there onwards, what is this? This is the depleted layer there. If it is not depleted, it will go like that, thin depletion layer, but when you apply voltage, when it will go up like that. So, the entire layer is depleted here. Here it is oxide. So, replace this with that. I have shown it thicker here just to enable me to draw this diagram. This can be thick or as thin or even thinner than that. So, between the two insulating layers here, this has epsilon r equal to 4, this has epsilon r equal to about 12, 12.8. So, for the same thickness, this will have larger capacitance, which would mean that coupling between the gate and the channel will be better. Okay. For a given voltage change here, the charge that will be here will be more. Q is equal to C into V. For a given V, if C is large, Q is large. That is what is happening here. Better coupling here. That means you can have better current, better transconductance. For a given delta V, delta Q will be more because capacitance is large. If delta Q is more, transconductance will be more. Okay. Delta Q by delta T is a current. If delta Q by delta T is large, current is large or GM is large. So, this device will have better transconductance compared to that. Now, 1-to-1 correspondence here. If a 1-to-1 correspondence here, this device will behave similar to the MOSFET IV characteristics. I do not have to derive that. This is equivalent of the inversion layer. When I apply VDS here, the inversion layer will start beginning to disappear at the end here. Similarly, when I apply VDS here, it is equivalent of applying negative voltage to that. Okay. So, charge will be reducing here. So, exactly same way you can derive the IV characteristics of this MOSFET, exactly similar to the MOSFET. All that you will have will be the MOSFET equation with C oxide replaced by the Cs, threshold voltage replaced by threshold voltage of this device, which we call it as off voltage. Okay. Mobility replaced by the mobility of this 2-dimensional electron gas, which will be tremendously large compared to that. If you go down to lower temperatures, this can be as high as 10 to the power of 5 or more centimeter square per volt second, whereas this will be just suffering from the lattice scattering as well as scattering from the impurity scattering. Impurity scattering is absent here, that is the benefit of this device. So, you can with one shot you can write down equation of the MOSFET, adapt it to this particular condition, and that is the equation that you see here. So, what we have written is the equation of the MOSFET exactly, because it is replaced the oxide with that depleted L-gas layer, and the channel immersion layer is replaced by the 2-dimensional electron gas. Mobility will be mobility of this electron gas, which is high. Cs is actually epsilon r epsilon 0 by thickness of that layer. Now, notice you would bargain for thinner layers. Why do you ask for thinner layer? Cs will be larger. If the Cs is larger, for a given change in voltage, ID will be large. Change in the ID will be large, which would mean GM will be large. We look forward to devices which have large GM, because the figure of merit of a device, any device for that matter, is GM by C. If GM is large, the FT will be large, cutoff frequency will be large. So, VGS minus V of whole square is a square law device. I do not know why they started putting this as V off, that is because usually it was depletion type of device, but we have seen just now that you can make this also announcement by making the V off positive, by reducing pinch off voltage. Delta ID by delta VGS is actually this quantity, this GM. Compared to the MOSFET, you can see that even at room temperature, this factor for MOS n channel MOSFET about 1000 mobility, all in centimeter square per volt second, and this will be at least about close to about 10,000, at 8,500, 9,000 that range, okay, very high. Plus this is, that is about a factor of about 8 to 9, let us say 8, and this is larger for the same thickness by a factor of at least 4 and 12.8, about 3. So, 9 into 3, 27, 25 to 30 times larger transconductance and mobility, which is fantastic that you can imagine. Okay, now we will see, we also argued out in the previous case of MESFET, when you go to higher and higher electric fields, the mobility will degrade because of field. Okay. But then you write everything in terms of the velocity, and then you can get the velocity overshoot benefits, which are very large. Okay. Just in this connection, I just also like to mention, suppose I go to very high fields, you get velocity overshoot effect, you get the transfer of electrons from the lower valley to upper valley. Suppose you have very high field, field is high, but voltage is small. I have a diagram like this. I would like you to just spend some time yourself, think about this thing. Conduction band is here, valence band is here, the electrons are there. This will be the gallium arsenide high electron mobility gas, which are located here, undoped, but there is a satellite valley here. This gap is something like how much? 0.3, 0.31 or 0.35, 0.36. In fact, people quote different values there depending upon the talk of this value or other value, 0.3, 0.35. I see different values quoted for that. Okay. So, definitely it is more about 0.3, 0.35. I think the value that I given was around this value. So, that is about that. So, suppose you have these channel electrons and the velocity field characteristic is like this. It goes up like that, What will be concerned will be when you go to short channels, you will have velocity more should everything will improve, that will be happy. So, because of this you get velocity which are in excess of 4 into 10 to the power 7 centimeter per second. Okay. Now, what I am trying to point out is this entire process of negative differential mobility dV by dE is negative, that is called negative differential mobility. This region occurs because electrons have transferred from here to here. Now, you can acquire high field if the channel length is very small and the voltage is less than 0.35 electron volts. Suppose the voltage is 0.3 volts, what is the energy of the electron? Q into V is energy. If voltage is 0.3 volts, energy is 0.3 electron volts. So, the electron has no chance to go into that layer. Now, you can see the beauty of the whole thing. You have electrons residing here, and you have the electrons which cannot acquire energy to go up to that point, and you have electrons which experience very high field. So, that means you are on this line. You are on this line, okay, your velocity can be much higher, but still do not have that. So, what happens is the electrons reside in the lower valley, and the entire transport takes place in the lower valley itself. Virtually people talk of the transport of electrons without intra-valley scattering. This is called intra-valley scattering. So, one scattering phenomenon is cut down, that reduction is cut down. So, it is a very high mobility right through all the way. V will be mu into E, that is all. Okay. That will be the type of velocity. Okay. So, you can get very high velocities in the short region. In fact, people even tend to call it as ballistic transport. Ballistic transport is actually a transport where there are no collisions, but there are collisions, lattice scattering is there, that is what governs the mobility. But you do not have this intra-valley collision or scattering. I just wanted to point out this to you that as you go to very short channels, if the voltage is low, you can still have high fields, high velocities, because the electrons remain in the lower valley itself. Okay. Put some number 0.3 volts applied across the channel, and channel length is say 0.3 microns. So, the field is 10 to the power of 4 volts per centimeter. The field is 10 to the power of 4. So, if you talk of this entire static characteristics here, you will think that is the velocity, because this 10 to the power of, this is 3 into 10. Oh, this is 10 to the power 4 is 10 kV per centimeter, somewhere there. This is 3 kV per centimeter. But you are not going to that curve, you are still remaining in this portion of the curve. You will get decided by the slope, what is velocity, because electrons do not have that energy. This is the irony of the whole thing. Okay. So, in devices which have 0.3 microns and 0.3 volts, you will have high fields, high velocities, because there is no intra-valley scattering. Even if you have 1 micron channel length, okay, you get just about here. Okay, this is just incidental. Now, just let me move on further with some of these discussions related to this Devices&Circuits. Now, we will just go through this whatever we have been saying. Enhancement and depletion mode type of devices are made by adjusting V p 0, because off voltage is V b I minus V p 0. I can reduce the V p 0 by reducing A, then V off can be made positive. So, if you go to this equation, reduce V p 0, because V p 0 is nothing but Q n d A squared by twice epsilon r epsilon 0. A I reduce, V p 0 reduce, the square of A. G m can be increased. Go back to the equation again. G m can be increased by increasing capacitance, better coupling, and capacitance can be increased by reducing the thickness of the insulating layer that is present between the gate and channel. So, GM can be increased by reducing A. Now, once you fix your threshold voltage or the off voltage by fixing Vp 0, if you reduce A, Vp 0 will fall. Okay. But you want to bring back the Vp 0, you must increase the doping. So, this can be done by increasing Nd for V of adjustment. I hope that statement is clear. Reduce A to get better transconductance, but you cannot get greedy and go on reducing A, because then you have to accompany it by increasing doping, and there is an upper limit on doping. The upper limit on the doping is, what is the upper limit? Schottky barrier diode. See, after all, just see this doping we are talking of. Reduce the thickness, but increase the doping so as to keep the pinch off voltage same. But upper limit is Schottky barrier. If you go to doping concentration 10^19, you will not have a Schottky barrier. You will have a bad Schottky barrier, leaky diode, and close to ohmic contact. So, the upper limit comes up by the doping concentration there. So, you are stuck up with that, and you are stuck with certain layer thickness. Okay. So, GM upper limit is there because of that. But of course, you can always play with the velocity, overshoot effect, and like very short channel lengths and very high fields to get high velocities, better transconductance. Now, the spacer layer. The spacer layer is, let me go back to the diagram once more. Top layer is doped, this layer is the spacer layer. We have put that layer there because we do not want these two-dimensional electron gas to suffer from the scattering. We do not want them anywhere near these impurity atoms. So, put a spacer layer which provides spatially separates the donors. Spacer layer separate the donors physically from these ions. Absolutely no contact, no Coulombic force of attraction, no scattering because of that. So, that is where put. Now, you can't make this too thick. People have seen that you make it thicker, it is better. Why? If you make it thicker, there is less chance of these electrons coming in under the effect of this dopants. So, you would like to make it thick, but the moment you make it thick, the total layer thickness, insulating layer thickness becomes more, and if it becomes more, CS falls, transconductance falls. So, that is an optimization there. So, people find that 20 angstroms is the one that you would prefer, and if you are grudging, you can say, okay, I want 30 or 40 angstroms. So, 20 angstroms improves mobility quite a bit. Okay, that is what we put. Now, this is what we have said already, GM in HEMT is much better than that of MOSFET, because mobility is 8 to 9 times larger, CSC is at least 3 times larger. So, at least 25 times better GM compared to MOSFET. Even when you have velocity overshoot, short channel length effects because of velocity overshoot effects and virtual transport without intra-valley scattering, you get much better performance, much better GM with HEMT. Okay. The other thing that we have been telling is the delta EC. We have taken the case where this x is about 0.4 or so, and delta EC is about 0.32 corresponding to that. Now, higher the delta EC, better ability to notch the electrons. You have got a well which is deeper, you can collect, it will collect more electrons there. Because after all, if you remember, the band bending of this lightly doped region is equal to built-in potential of the homojunction plus delta EC by Q. So, if delta E c is higher, more is the band bending. If more is the band bending, more will be the electrons. So, that is what is implied here. The 2D electron concentration is higher if delta E c is higher. From that point of view, you would like to have a device which has got higher delta E c. But there is an upper limit for the delta E c with L-gas gas system. What does delta E c depend upon? Delta E c depends upon X mole fraction of aluminum. So, higher this aluminum concentration, higher will be delta E c. Virtually 0.66 times delta Eg1 minus Eg2. Eg1 is band gap of L-gas, that is higher if mole fraction is higher. But there is an upper limit because higher aluminum content introduces some trap levels which actually affects the total performance of the device. Okay. The trap levels will be present in that layer and they seem to trap some of these electrons without releasing them to the channel itself. Okay. The electrons are trapped there, they are not available for you to the channel. So, even if you increase, there is no benefit. 1. Okay. You may say, okay, I will still tolerate with the thing, but it gives rise to poor performance at lower temperatures, because more trapping takes place. Second one is, it is difficult to make ohmic contact onto wider band gap materials. So, you will have to put another material on L-gas which has a lower band gap to make the source drain contact. Source drain contact is ohmic contact. It is always difficult to make ohmic contact onto wider band gap semiconductor. That I think we have understood it long time back, because if it is a wider band gap material, okay, the phi Bn will be 2/3 of that if it is, that is large. That way you can understand it. So, easy to understand that way. So, you have higher band gap means difficult to make higher phi Bn, which is difficult to make ohmic contact. So, the technology suffers from this difficulty. So, the technologist puts hands up immediately and says there is upper limit, and added to that this performance limitation because of this center which is called DX center. I do not know why they call it DX center, it is a trap center. Okay. There are usually funny ways of naming some of these devices and some of the behaviors. Okay. So, this is the DX center, it is a trap level. So, there is upper limit of that, usually they limit it to about 0.3, that is the X of about 0.3, not even go to 0.4, which will be giving you delta is less than 0.3 electron volt. Okay. Now, about the spacer layer, undoped layer thickness. These are some of the experimental points people have made. Okay. I think the Illinois University or so, they have made some of these measurements. So, this is the maximum current that you can get as the spacer layer thickness is varied. That is understandable, ID is proportional to Cs. Spacer layer is thicker, Cs falls, ID falls. ID is the maximum current, means actually when the band bending is maximum. If a forward bias diode junction, the band bending in the gallium arsenide layer reduces. Okay. You can even remove all the electrons, it goes off, go to the off state. It is fully on, the device is fully on, maximum current that you can get is this, about 300, that is what they have seen. This is of course some theoretical computation that they have made, that is what was expected, but they have seen this. But of course, they do claim that these are not the final, there may be many more points to be filled up here. Okay, the particular literature that I have, these are values which are there. I am sure some more points would have been fitted into that, but the truth is that thinner it is the better. Okay. So, they use about 20 angstroms, so that you get the best result. So, this is summing up what we have said now. For desired large current levels, smaller electron donor separation, that is a spacer layer, is needed. Reduce the spacer layer or the setback layer, both names are there, you better get electron concentration. That is just I am repeating what is said here in this diagram in the form of words. Available data shows some results, maybe many points, more points are required to fit in better. Maximum current levels of about 300 milliamperes at 300 K in MOSFET with 1 micron gate and 1 millimeter gate width have been observed. Okay, this is actually what is reported for L-gas system. You can get better if you can have a material which has a better delta EC. You have to switch over from gallium arsenide based material to maybe to indium phosphide based materials. We will see later at least some examples of that. What the impact of indium phosphide based devices, we will see that little later. This is actually to show you that this is a reality. The device is a reality, device have been made and tested at room temperature. These curves 1, 2, 3 curves, they are at room temperature. Okay, the red curves. The blue ones 1, 2, 3, they are at 77 degree Kelvin. The x axis is 10 milliampere per division, 10, 20, 30, 40, 50 milliamperes. The y axis is 0.5 volts per division, 0.5, 1, 1.5 like that. Okay. That is VDS. This is ID. In the case it is missing here, it is understood that drain IV characteristic title is there, drain current versus drain voltage, output characteristics of the device as VGS is varied. The gate voltage VG1, VG2, VG3 in steps of 0.2 volts per division. Okay. So, if this is 0.2, 0.4, 0.6 volts steps. So, for 2 temperature is given. I would like you to observe this characteristic carefully. There are 2 things to observe. One, the spacing between the 2 curves is more. See, for 0.2 volts the spacing is that much there, which is almost about 2 divisions, that is about 20 milliamperes almost in that range. Whereas, if you take these 2 curves for the same voltage difference of 0.2 volts, it is slightly more than 1 division. So, it is not double the current, but almost double. Okay. So, what we are telling is the change in current in the case at 77 degrees Kelvin is more than the change in current for the same change in voltage at 300 Kelvin, implying what is the reason? The reason is what we have been telling all along, mobility is higher at lower temperature. Mobility at room temperature may be something like 8500 best. Okay. At 77, 100,000 centimeter square per volt second, tremendous improvement is there. Okay. 10 to the power of 5 centimeter per second. That is about the range that people talk of. So, you get much better performance. But this will have combined effect of the mobility and also when you go to higher field here, high field. We are talking of 1 micron channel length, you will have velocity overshoot effects. You will not get the full benefit of mobility. That is why you do not get that complete factor as much as you expect 25, but you get much higher factor. So, just go to next slide, you will see the values. The extrinsic transconductance at 77 degrees Kelvin is about 400 millisiemens per millimeter. Per millimeter is implying gate width is or channel width is 1 millimeter. Millisiemens is milliamperes per volt. At room temperature it is 225 millisiemens per millimeter. Okay. So, it is a tremendous benefit that you get, which will tell you that the cutoff frequency when you take it up will be much higher. Okay. Now, the improvement in the drain current. Now, one more thing I want you to notice here, which I have not listed out there in the slide, is notice the characteristics at this portion. At this portion, I will just go to the board and put that out, so that it becomes much more clearer. I will plot one characteristic, VDS versus ID. To avoid confusion, I will plot one characteristic. The at room temperature, you have that characteristic. If you have for VG VGS equal to say 0.4 volts. For same VGS, no doubt you get higher current. You also get that sort of characteristics. This is VGS equals 0.4 volts. What I mean is VGS minus V threshold, whatever it is, some value I am putting arbitrarily, and this is at 300 degree Kelvin, and this is at 77 degrees Kelvin. Okay. This is at 300 degrees Kelvin, and this is at 77 degrees Kelvin. You can see the benefit here. So, not merely you get better transconductance, you also get better smaller on resistance. For digital circuits, it is really required. You want to have the on resistance smaller. Just see here, if I put a load here like that, if I put a load resistance like this, you will end up for the same gate voltage here in on state, whereas here you will end up here. So, this is a drop in on state, this is a drop, much lower drop, power dissipation will be smaller, okay, and the frequency response of the circuit will be much better, because charging times are all smaller, because resistance are smaller on the resistances. So, we have seen right in the first 1 or 2 lectures when we discussed, it is the theme of these high speed devices is to go to smaller state capacitances, etc., smaller capacitances, smaller resistances, that we achieve here. But of course, we have to put up with going down to lower temperatures. Okay. So, this is one key thing that for these high electromobility transistors, apart from better transconductance, lower on resistance. Now, one more thing that you notice here is, if you go to the next slide, you will see that there is a shift in the threshold voltage. These are transfer characteristics. What we have shown there is output characteristics. These are the real devices people have measured. Okay. So, you can see this curve, red curve gives you the transfer characteristics, IDS versus VGS at room 300 degrees Kelvin, and this curve gives you at 77 degrees Kelvin. Two things you have to observe. One is this is having sharper, steeply increasing, indicating for a given voltage current is larger, GM is larger, okay, because mobility is larger. Other thing is that the shift in threshold voltage to the positive side. Okay. So, the shift in threshold voltage is because of some of the trapping of the electrons in the L-gas layer at lower temperature, okay, and slight amount of carrier freezing also takes place in L-gas. Okay. The improvement in drain current observed should be much larger. See, what I am saying is, I am sorry, if this threshold voltage remains there, same value, when you apply the gate voltage, if you shift this entire curve there, okay, see, suppose I take VGS versus ID saturation. In the first curve, we have got like that. Let me just put it slightly differently. If I have got, that is square law. If the threshold voltage remained the same, you would have got it like this. Because for the same change in the gate voltage, current is much more. VGS minus V threshold into the mobility. VGS minus V threshold square into mobility or other terms. Mobility is better. So, if VGS minus V threshold remains same, I would have got better current. But what happens is the threshold voltage, this is at 300 K, this is at 77 degree K. If V off does not change. If it does not change, that is what you will get. That is what is the meaning of that particular term that we put there. Okay. But in practice, when you go to lower temperature, you do not have all those electrons available, because some of them are trapped in defects in the gas, or freeze out also you can say. So, this gets shifted down here. So, that will go like that. So, what is mentioned here is you would have got better current there if the threshold voltage had not changed, because it has become positive. Okay, the current is only that much changing. That is the meaning of that. Here there is some portion where it is even lower, but when you go to some other portion, but it is better to take a look at this real curve that they have given. So, you can see at this point, if you see, the current is smaller, because threshold has shifted to the right because of the non availability of the electrons there. Okay. So, it is like, okay, these are some of the things that people have observed and seen for themselves, that the high electron mobility transistor is not a myth, it is a reality. Way back they have realized it. Okay. Other thing that you can see is the threshold voltage shift is not only due to the defects, it is also due to some carrier freeze out in the gas layer. The carriers are frozen out, they are not available for transfer onto the two dimensional gas. Their current is proportional to gate voltage away from the cutoff. Okay. Near cutoff, linear cutoff, actually the well widens and you get much nonlinear. See, what is the statement there meaning is, you get the regular square law characteristic, but here you have got much more nonlinearity, because as you go to near the off state, as you go nearer to the off state, what happens? You have got that layer like this, that is in the fully on state. This is a perfect quantum well which confines these electrons, but as you go to the off state, what happens? This is brought down by the forward voltage. So, this is on fully, that is off state. This is brought down by an amount, let me just draw it slightly better. Okay. Off state is like that. This is the delta EC. Delta EC by Q. So, this is spread out here. So, the confinement is not as good as in this case, they are spread out there. That is why that the deviation from the regular characteristic comes up and more nonlinear behavior is seen around this portion. That is the meaning of that. In fact, that is actually the should be given as a figure caption for this, that is given on the next page. Okay. The confining is of electrons in the notch is not as good, that is the implication. From the transfer characteristics, from this we extract the transconductance Gm delta ID by delta Vgs, that is this. You can see that the threshold voltage has shifted to the positive side, just like in the transfer characteristics, it is actually deduced from there. Threshold voltage shifted to the right because of electrons not being available due to trapping and also carrier freeze out. Okay. And this is steep, it is not as steep. Transconductance is about 400 millisiemens per millimeter, transconductance is about 225. What we are trying to point out here is, whatever we have said now originally we have got in the form of figure. Transconductance That is, from output characteristics itself it was evident that the spacing between the characteristics is more, which would mean the delta I d by delta V g s is more. That is why this is sharper. And we do not have to explain further the shift in the threshold voltage, because we have explained that already as due to carrier trapping, okay, and carrier phase out. One thing that one should note here is, this as you go up here to larger and larger voltage, the transconductance increases, okay, because V g s minus V off is increasing, number of electrons are increasing, but then afterwards it does not increase that steeply, it gradually tapers off. It tapers off because the mobility of the electrons tends to fall down. In the case of MOSFET also you will see that, because of the high field effects, field effect in the vertical direction. Okay. And in this case there is an added effect, that is we are talking of this portion, a slight tapering off or the rate of increase of the transconductance reduces, that is because the electrons, okay, the electrons which are usually present here, as you go on to higher and higher VGS, what you are happening is you are going closer and closer to that, and the electrons have got two subbands. Okay. It will fill up these levels first, it will go to these levels afterwards. More and more will get filled up here as you go to more and more voltages, gate voltage. Okay. And these levels, in these levels the electron mobility is slightly smaller than this. Go to the higher energy, okay, you have lower momentum. In fact, you can see those curves which have, you go up in the momentum curve, the effective mass slightly falls here. So, because of the fall in the mobility, the transconductance is not as high. Okay. What we are telling is, go to higher concentrations, the second subband gets filled up. When you go to higher voltages, near 0.7 volts gate voltage, the second subband gets filled up, and there the mobility is lower. Number 2, if you go on increasing the bias in the forward direction, what will happen? This statement, undepleting the doped L-gas aggregate may happen. Okay. I will have to point out that to you. See, if you see here, I have this L-gas layer, okay, and I have the gallium arsenide layer undoped. This is N plus. I call it N plus to ensure that it is rather highly doped. Now, semi insulating gallium arsenide. Okay. Those are the electrons, N plus the gate. Okay. That is the gate. I keep on making it more and more positive. Okay. What happens? You keep on making more and more positive, of course, you have more and more electrons here. But at a point, what will happen to the depletion layer of this? See, there should be a minimum voltage across this layer, negative with respect to this substrate, so that entire layer is pinched off. Now, you keep on making it positive. See, I need, if I had only this particular layer, VBI minus VP0 is the voltage that is required to pinch off. Okay. And I have need certain voltage to remove these charges here. What you are going is in opposite direction, making this voltage more and more positive. As you keep on making more and more positive, a situation will come where the depletion layer will open up here. Still you will have charges here. you will have a situation where, let me just draw it side by side, where the that is there. I keep on reducing the voltage, make it more and more positive, this will keep on moving up, but this will actually keep on becoming flatter and flatter. This is plus minus here, I am making this positive with respect to the whole thing. So, this will keep on coming like this, and at a certain point it will open up here. Okay. It will just open up here like that. If it opens up, that is bad news, because the current transport will take place through that layer which is opened up. If that is opened up layer, there will be channel for current flow through heavily doped layer. Heavily doped layer is mobility is low. So, that is what is implied by saying, in fact, we can, since we have discussed in detail how the depletion layer moves with applied voltages, you can easily grasp that when apply plus voltage, ultimately the channel will open up, and when it opens up, the conduction will take place through the undepleted portion, okay? And this creates new conduction path through the inferior quality gas. That is inferior quality compared to this notch, electrons in the notch. Okay, now, in summary, parameters which you can optimize. Today, I think we will wind up with our discussion on gas system, Indium phosphide based system. Maybe we may have to meet again next lecture, but now we will summarize few things. Aluminum concentration is the one thing that you have to optimize. Doping concentration and thickness of the gas layer. Aluminum concentration here, let me just remove this to keep it all the time in perspective. That is the layer, this is the thickness A, and that is the doping, and this is X, A and D. They are the parameters which you have to optimize. X, there is an upper limit of about 0.3 or so. Okay. People do not use, you go beyond 0.3 because of the traps which are introduced, because of difficulty in making UV contact onto that layer. Okay. Now, doping is the upper limit, because Schottky will start conducting. So, the maximum doping is about 10 to the power 18. Correspondingly, you can go down to lower A for a given threshold voltage. So, there is a lower limit on A and upper limit of ND. Upper limit 10 to the power 18. Now, depending upon your threshold voltage, you choose this A. You can't go beyond that for ND. Higher X gives higher barrier height, all those things we have discussed, Schottky, and also gives higher delta AC. Yeah, okay. Higher X you need because it gives you better higher delta AC and better carrier concentration, but you can't tolerate that because of the traps which are being introduced and band gap. So, X is about 0.3. To maximize GM and ID, A must be as small as possible, accompanied by increase in doping. Lower limit of A is set by upper limit on ND. The moment you say 10 to the power 18 is upper limit of an ND, then the lower limit is set by that for a given threshold voltage. Maximum voltage VGS, what is the maximum voltage that you can apply to the VGS? This is what we have been just now telling. You go on applying more and more voltage to VGS, you will get of course more and more charge VGS, but at a particular point that aluminum gallium arsenide layer will open up. At that point, do not have any control beyond that point. The transport will take place through that doped layer. Okay. This is about 0.8 volts at 300, okay, and 1 volt at 77. In fact, it can be, the limit can be 2. The VGS that you apply, upper limit is for 2 reasons. One, the gas layer conducting. Number 2, Schottky barrier followed by conduction. Okay, that also can happen. Any one of them can happen. So, about 0.8 volts is generally that is said for the depletion type of devices. If you go to a non-FEM mode type of device, the limits are lower, because the Schottky start conducting easily. Setback layer 20 angstroms to keep GM high, that is that undoped spacer layer. Its spacer layer is also called as setback layer, that is about that. Typical values normally of MOSFETs are 10 to the 18 centimeter cubed for the L-gas layer doping, thickness about 350 angstroms, okay, and that X mole fraction of aluminum is 0.3, and setback layer is 20 to 40 angstroms. So, we will actually wind up the discussion on this HEMT or based on L-gas today, but we will take a look at materials like indium phosphide. We will explain why we should go for that, etc. in next lecture. Okay.